Oh, welcome everybody to the fourth FACS case study in our autumn webinar series. I'm delighted to be able to introduce Amy Crawford, to talk about a really interesting trial that Berry consultants have been involved in, the enrich trial. We don't have too many talks about actual patient enrichment trials, so this one's quite unique. So, Amy, would you like to take it away?
Sure. Thanks, Tom. Yep. All right. So this is a trial that Berry Consultants was involved with for the design and implementation. I did not personally design or implement this trial. So we have a couple experts on the line, I think, who can answer really specific questions if we have any, in particular, Dr. Giorgio Pollin. But this is the design team, the statistical analysis committee listed here. And we'd just like to acknowledge the DSMB for this trial, the academic investigators, the sponsor, and of course, all the patients, families, and clinicians who participated. I'd also like to acknowledge Kurt Bailey and Nick Berry, who provided some enrichment materials and FACS support along the way. So yeah, we'll go ahead and get started. So like Tom said, we don't often get to talk a lot about these patient enrichment designs. So I'm going to start today with just a quick primer on what enrichment designs are, how they typically run, the way that we think about them before I dig into the enrich trial specifically. That was a trial in hemorrhagic stroke. So we'll talk a little bit about the indication, but then I'll tee up the design in the slides here, and then we'll move into FACS and we'll put that design into FACS, look at it there. Look at a few simulation results, and then enrich is a trial that is complete. The results are published, and so we'll actually come back to the slides at the end and look at what those results were, how they aligned with some of our simulation assumptions, and so on. Okay, so a little primer on enrichment trials. Enrichment trials are trials that adapt the inclusion-exclusion criteria along the way. So ideally, we design a trial with a clear expectation of who will benefit, and we can write down our inclusion-exclusion criteria accordingly. We have a good idea of what our patient population should be for our randomization, for our enrollment. However, there are situations where there is uncertainty around the population who will benefit, and those are the situations in which we would want to adapt our patient population based on accumulating trial information. Okay, so that's the uncertainty we're trying to handle. Enrichment trials can really help us mitigate two risks. And I've got a picture here for you to kind of describe this. You can think of this whole oval as your entire patient population. And in the patient population, there's going to be a section of patients who do not benefit from the intervention. That's represented here by white. A section of patients who will benefit from the intervention, represented over here by yellow. And it would be fantastic if we knew exactly where that line was drawn, but oftentimes we don't. And so there are some risks with setting up your inclusion-exclusion criteria, right? You could enroll too narrowly. For example, if you enrolled this trial population over here, sort of a subset of the yellow, you're going to maybe miss people who could have benefited from your therapy. You're going to have an indication that's smaller than it could have been. It might take you a long time to enroll this trial because you've got these people coming in and you're going to end up screen failing a lot of them. You've got a narrow set of patients that you're targeting. The opposite risk is that the trial enrolls too broadly. So you can think of a trial that has a population definition that looks like this red box, where you're enrolling a lot of people who benefit, a lot of yellow. You're also enrolling a lot of people who do not benefit, so a lot of white. This comes with dilution of the treatment effect. You can imagine if the people in this white space are non-responders and you get a lot of them in your trial, you may not be as powered as you would have hoped to run that trial. This has downstream effects. You're going to end up, if this is a phase 2 trial, for example, doing a lot of subgroup analyses, trying to figure out what's the right thing to do in phase 3, picking through your data, and you're going to continue to have some uncertainty about what that trial population looks like. So the basic idea behind enrichment is to, dynamically sort of as the trial moves on, adjust where this red boundary is. That's the big idea. So how this works is you begin with a subset of the population. So you define sort of a burn-in inclusion-exclusion criteria, and you conduct frequent interim analyses as you go in your trial. And on each analysis, you're going to assess which subgroups appear to benefit. What we're going to talk about today, what the enriched trial does, is it discontinues poorly performing subgroups. And I think when we see enrichment trials, this tends to be the process where you kind of start wider. You think you have an idea of who will benefit, but you're maybe worried about a subgroup that might not, and you discontinue poorly performing subgroups. There are enrichment trials where you add new subgroups, but I'm not going to focus on that today. But what happens then is as you discontinue poorly performing subgroups in your trial, the trial is going to gradually focus on the subgroups where the therapy is effective, and you're going to be kind of honing in on that patient population where your therapy works and can provide benefit. Okay, so a little toy example here. This is a schematic with let's see, subgroup A and B. Subgroup A represented by the lighter shaded stick figures, subgroup B by the darker shaded stick figures. And so what you can see in this trial, a control arm and a treatment arm, the trial starts randomizing with all comers. So subgroups A and B, the wider trial population. Maybe we schedule an interim analysis, 10 patients in, we evaluate the data, we say, okay, we don't have enough evidence to stop a subgroup, let's continue randomizing as planned. We do another interim analysis, and at this analysis, it looks like subgroup B is performing poorly. So we make the decision to stop enrolling subgroup B. We adapt our inclusion-exclusion criteria to include now only subgroup A patients, and we continue with those patients alone for the remainder of the trial. You can imagine this has implications on accrual rates, a lot of things, but one big one that we like to think about with enrichment trials is accrual rates. If subgroup A is less prevalent than subgroup B, this second half of your trial could take a lot longer to enroll than the first half of your trial. You could focus recruitment efforts on subgroup A, but a lot of times there's just sort of no helping, who walks through the door. So there are a lot of things to think about when we're designing these trials. Things like, interim timing, enrollment, a lot of things like that. The beauty of it, though, is that simulation can help us assess all of those and the decisions that we make and the impact on trial conduct. Okay, so when we get to the end of the trial, we want to analyze our data. There are a few different approaches that people take to analyzing data in enrichment trials. You can imagine it would be really natural when you get to the end of this trial, say, well, we identified subgroup A as sort of a responding subgroup. I want to analyze subgroup A. I think that that's the subgroup where my therapy works, and that's what I want my primary analysis to be. So that might look something like this, right, where we take out the subgroup B people and pool the remaining subgroup only. So we pool all of these blue people for the treatment group and the green people for the control group. Has a really natural interpretation because now you've dropped out the subgroup that you've identified at the interim analysis that is not responding. But this has some cherry picking implications, right? You're cherry picking the subgroup of patients in your trial that you want to analyze. There's multiplicity. You've now increased your chance of type 1 error. Okay, so that's one drawback of this analysis strategy. What we're going to talk about with Enrich is actually the second one, which is pool all randomized patients. So that would leave these subgroup B patients in the picture. You pool all the blue on the top for control, pool all the green on the bottom for treatment. When you do your primary analysis, you're probably going to get some dilution of your treatment effect. And if you're in a mixed efficacy scenario, like the one that's shown in the picture, but what you get out of this is this nice statistical property of strong controlled type 1 error in the joint null scenario. So if both subgroups have a null, no effect, you get your type 1 error there if you include all of these people in your analysis. And that's what the Enrich trial did. So that's what we're going to focus on here today. So you can imagine another consideration here is, you want to make enrichment decisions early if you're taking this analysis approach, because the earlier you can make a good decision, right, the fewer subgroup B people you can include in your analysis, and you can sort of avoid some dilution of your treatment effect. However, the earlier you start to make your decisions, the more mistakes you might make based on small amounts of data. So that's another thing simulation can help us with, is when to schedule that first interim analysis and things like that. And I should have said this before, but please feel free to interrupt with questions at any time.
If you ask in the Q&A, I will relate them to Amy while she's talking.
Okay, thanks, Nick. So there are other approaches to analyzing enrichment trials. You could do something in between the two options that I just talked about. For example, you could use a Bayesian hierarchical model that borrows information from the responding and non-responding subgroups, according to how much those that the subgroups agree. So this would be something we refer to as dynamic borrowing. Okay, so let's get into the actual case study, Enrich here. Enrich, like I said, it ran. There are results. So here are the two main publications from Enrich. The publication on the left came out in March 2023. This is the study protocol publication. And I believe the adaptive design report that was developed at Berry Consultants is an appendix to this, or a supplemental material to this publication. So you could find that there. This publication on the right came out in 2024. This is the results publication in the New England Journal of Medicine. So you can look through those if you'd like more information. But I'm going to walk you through the design here, and then we'll put it into facts.
Before you move forward, we have a question.
Okay.
Going back to the two ways to fit your primary analysis model, the two populations. Is the impact on the type 1 error rate substantial in the first approach, the cherry picking approach? And what are the main factors that might affect overall type 1 error other than timing of the interim analyses?
Yeah, that's a good question. So the impact of type 1 error can be more substantial or less substantial, kind of depends on what happens in the trial. What we find is that if you cherry pick a really small subgroup, so let's say in this picture, subgroup A was like 25% of your prevalence, and subgroup B was 75% of your population. And we pick subgroup A and we do it late in the trial. That can have a larger impact. It's sort of more influential cherry picking on type 1 error than if you have more equal subgroups, or if you pick one of the larger subgroups. So Dawn actually used this the Dawn trial, used this analysis approach, and Todd Graves at Berry Consultants has a nice formula that aims to handle this increased chance of type 1 error. So you can find more information in the Dawn study. Sorry, what was the second part of the question?
What other adaptations or parts of the trial can increase type 1 error other than timing of interim analyses?
Okay, yeah. So I think that's also related to prevalence. I'm not thinking of any others right off the top of my head.
Accrual rate,
but of course,
if you have interims, things like that.
Yeah, accrual rate. Of course, if you have other adaptations going on here, which the Enrich trial does, has early success stopping and things like that, you'll need to do some type 1 error control for other adaptations as well. A lot of times enrichment isn't only enrichment. Enrichment trials include other adaptations. So a lot of this gets kind of rolled together.
Thanks. That's it.
Okay. Thank you. Okay, so the Enrich trial enrolled patients with intracerebral hemorrhage we call this ICH. Intracerebral hemorrhage happens when a vessel ruptures and bleeds into the surrounding brain tissue. These are strokes. The blood can negatively impact the brain tissue. What happens is this blood that's pooling in the brain can put pressure on the brain, which is bad. The brain behind the burst vessel, is now deprived of oxygen-rich blood. So these are bad strokes. All strokes are bad. These are very bad strokes. And an ICH can occur in different locations of the brain. So you can imagine that we're going to talk about a surgical procedure. Different locations of the brain may be more or less easy to get to with a minimally invasive surgery. We may expect differential treatment effect based on the location of the ICH in the brain. And so the location of the ICH is actually going to be the subgroup with which we make enrichment decisions. So the ENRICH trial was designed to overcome limitations of prior ICH evacuation procedures. There were previous studies in this space. I'm not going to get into it. The MISTY trials, the STITCH trials. What ENRICH is doing a little differently, or what they did differently, was they focused on early intervention. So patients were randomized within 24 hours of last seen well from their stroke. They are using this minimally invasive surgery, which we'll call MIPS. This is the intervention that we're going to test, and focusing on maximum clot removal. So I'll just touch briefly on a couple things on this slide. I elaborate on a lot of them coming up, but the background for this trial, one interesting thing here is this trial is IDE exempt. So it was designed with statistical rigor, but it was designed to improve and inform clinical practice. So there weren't regulatory interactions, as far as I'm aware, with this trial, but it was rigorously designed. The eligibility criteria included ICH, so strokes in the lobar or anterior basal ganglia regions of the brain. These are our two locations, so lobar and ABG. The trial ran from December 2016 through August 2022, and there are two treatment groups that it looked at with one-to-one randomization: medical management and MIPS, that surgery, plus medical management. So a little more on the treatment arm. So the medical management group followed the standard guidelines, and then MIPS is this minimally invasive procedure. Okay, the primary endpoint in this study is the utility-weighted modified Rankin scale, evaluated at 180 days. This, what we look at for this is the mean difference between treatment groups. So if the average and high is good, you want a high utility weight. If the average utility weight for the treatment group is higher than the average utility weight for the control group, we might think that the therapy, the minimally invasive surgery, provides benefit to patients. This utility weighting structure expresses the desirability of a specific outcome to a patient in society. So there's a paper on this utility weights. But what's usually done in stroke, and what has been kind of historically done in stroke, is patients are evaluated on this MRS scale, the modified Rankin scale. It's a scale that goes from 0 to 6, where 0 is no symptoms and 6 is death. What the utility weights do is it assigns a weight between 0 and 1 to each of these ordinal outcomes, and 5 and 6 in the utility weight are both considered to have a utility of 0. So this severe disability, this tends to be a vegetative state. The consideration here to patient and society is that has the same utility as death. So we're going to be working on the utility weighted scale. We're going to treat the endpoint as continuous, and we're going to measure it at 180 days. It's the primary outcome. We're also going to measure it at 90 days, so halfway through. So we have a 3-month and a 6-month observation, and we can use our early outcomes, our 3-month observations, to inform our 6-month observations. There tends to be a lot of correlation in this outcome over time between 3 and 6 months. The trial used an adaptive sample size. It took a Goldilocks approach. So this is the sample size algorithm developed by Christine Broglio and others. The goal with the Goldilocks approach, and I'm not going to focus on this, but it's to get the sample size right, not too small, not too big. So what happens at every interim analysis is we evaluate the enrichment criteria, which I'll show you in just a second. We evaluate the enrichment criteria. We also ask, should we stop enrollment? Should we stop at this sample size? Is this the appropriate sample size for the study? The sample size can be anywhere from 150 to 300 patients. We do interim analyses every 25. We can stop for success or futility. If accrual stops for expected success, we don't immediately do an analysis. We wait 180 days for all the patients who are randomized to have the opportunity to observe their primary endpoint, the 180-day MRS, and then we perform the final analysis. So that's the Goldilocks style sample size selection algorithm. The enrichment is the interesting part, right? That's what we want to talk about. The enrichment here happens by hemorrhage location. So ABG and lobar. So in this diagram, you can see the trial is enrolling equally ABG, lobar to medical management and the intervention. And at some point along here, enrichment happened and the lobar location was dropped. The trial continues to enroll ABG only. And when we get to the final analysis, because we're using this analysis strategy that pools all of the data together, we have a little bit of lobar and more ABG for the comparison of medical management, guideline-based medical management versus MIPS plus medical management. So what does this all look like put together? So here's the trial scheme. You can see these are the interim analyses. We said we were going to do interim analyses starting at 150 patients randomized all the way up to 275. If you don't stop early by 275, the maximum sample size is 300. At the interim analysis, we can take 3 actions. I guess the fourth one, if none of the 3 actions are met. We can stop accrual to one location, that's ABG or lobar, for futility. This is an enrichment decision. We're changing the inclusion-exclusion criteria, restricting future enrollment. If the criteria are met to stop both locations for futility, so if we want to sort of enrich on both locations and drop both of them for futility, that is going to be our trial-wide futility rule. We can also stop accrual in the trial for expected success. And if you don't do one of these 3 things, then you just proceed on to the next interim analysis. You randomize 25 more patients with no modifications. Once you stop accrual, whether it's by getting to 300 maximum sample size or by stopping early, you wait 180 days, allow all your participants to have the opportunity to observe their primary endpoint and conduct your final analysis. There are a couple additional guardrails in this study. Locations can't be dropped, so that's the enrichment rule, until 30 patients in the location has complete 180-day outcomes. And the trial cannot stop early for success until 60 patients have complete 180-day outcomes. So I'll show you where those go in facts, but those are some minimum amounts of information that this study has, the design has, sort of as guardrails, so we're not stopping too early based on a very small amount of information. Okay, a little bit of math here. The utility weighted MRS at 6 months, this is our primary endpoint. Like I said, we're going to treat this as a normal, continuous endpoint. So these observations, we're going to allow them to follow a normal model with a mean based on the subgroup that the patient is in, ABG or lobar. So G here is not treatment group, it is enrichment group, and some standard deviation, sigma. At the interim analyses, we're going to use a hierarchical model because what we need here is we need an estimate of the treatment effect in each subgroup. And that estimate is going to be called theta G. This is what FACS calls it as well. So the structure of this model is so that we get a control estimation for each subgroup, gamma G, and a treatment effect estimate for each location, theta G. We're going to let that theta G follow a hierarchical prior structure with a mean and a tau. Tau is going to control the amount of borrowing between the locations. So it's going to control how similar or dissimilar the theta Gs are. So theta G is a big quantity of interest for us here. Theta is also a quantity of interest for us here. This is the pooled model. So FACS calls this the across groups model. And what this does is it's a single treatment effect. So we still get a control rate for each subgroup, but we assume that the treatment has the same effect across subgroups, across hemorrhage locations. And we put a very diffuse, non-informative prior on theta. So this model, this pooled model, this is what we're going to use to assess success, the success rule, and the early success rule. Do we want to stop the sample size early for success? And we're going to use that theta, the pooled model theta, to determine final success, because like we said, we're taking this analysis strategy that pools all of the patients that are randomized together for the primary analysis. So the decision-making quantities, we have a superiority decision here to make using theta. If that if the across group treatment effect, if the posterior probability that the across group treatment effect is greater than 0 is bigger than 0.99, we'll stop accrual early in the trial for expected success. Once we get to the final analysis, if that posterior probability is a point above 0.975, that is going to be our sort of decision-making quantity. And we would say, yes, the MIPS device is successful, superior to medical management alone. So that's our final success criteria.
Will you elaborate a little bit more on expected success? There's a question asking that. And is it the same as testing for overwhelming efficacy?
Sure. So expected success here, a lot of times when we think about like a Goldilocks approach, and it's not quite the same as like a group sequential approach, a lot of times we use predictive probabilities, and we say we predict that we'll be successful here. We're using posterior probabilities in this rule, not predictive probabilities. But the idea behind expected success is if we get to an interim analysis and the posterior probability that the therapy is superior to medical management across the whole population is very high, overwhelmingly high, 0.99, that is a signal to the trial, a trigger that says, okay, stop accrual. You don't need to experiment on any more people. It's highly likely that if you stop now and you follow patients up, you will meet success in your trial. So that's the way we're using that rule. I don't know about the phrase overwhelming efficacy. It's not meeting that early rule, that 0.99. It's not the same as a group sequential design where you say, stop, we met the primary analysis. You could think of a p-value less than 0.025 or some group sequential, adjusted value. Stop now, success. What this rule is telling us, so it's not that. It's telling us stop accrual, and it separates the primary analysis from the decision to stop accrual. So it says, we think it's likely you'll be successful if you stop now and follow up all the patients. I hope that answered the question.
Yeah, thanks.
Okay. So success decisions are based on this across group theta, because that's what our primary analysis is based on, the pooled across group data. When we're making decisions to stop a certain location for futility, this is our enrichment, we want to use this group specific thetas. This comes from the hierarchical interim model. And what we want to ask about these group specific thetas is about the posterior probability that we observe some clinically meaningful benefit in the subgroup. And the clinically meaningful benefit is defined by this 0.075. This was done, as far as I understand, with collaboration with clinicians. I don't know exactly how they got to this 0.075 number, but if the probability the posterior probability of demonstrating clinically meaningful benefit in a subgroup is low, less than 0.2, then we would drop that subgroup, that location, for futility. That would be an enrichment decision. It's the same rule in lobar. We call this a super superiority rule, right? Because this value here is a super superiority margin. It's not zero, this 0.075. Again, if we drop both groups for enrichment, that's our futility rule in the trial-wide futility rule. Okay, we're almost in facts, I promise. Okay, a little bit more about assumptions. So in this trial, like I said, there were some previous studies that happened, the Stitch and Misty trials. There was control information on the distribution of MRS at 180 days from these trials. And so what Enrich did was they looked at these publications, they looked at the data, and they tried to figure out what is the control rate that we expect to see for the MRS outcome. And here's their expected distribution highlighted in yellow. And then they can apply the utility weights to get to the utility weighted MRS scale. I'm not going to go into a lot of details about that. But what they did was they did that, and then they found that the standard deviation of this continuous outcome, once we're on the utility weighted scale, tends to be 0.338. And so that's the assumption that we're using, that we'll use in facts, the standard deviation for the observations. The treatment effects are maybe a little bit more interesting here. This is a difference in means on the utility weighted scale. So null is going to be 0, no difference between treatment and control. Small, 0.15, medium, 0.18, large, 0.21. And the interesting scenarios in the enrichment design are going to be mixed scenarios, I think, right? Where one subgroup has a medium effect and one has a null effect, for example. So we'll look at that in facts. A few other settings briefly before we go there. This study, before it started enrolling, wanted to look at accrual rates of 5, 15, and 30 patients per month. I just talked through the MRS control distributions. They weren't expecting a lot of dropout, so they simulated the design with 0% and 10% dropout. They were expecting prevalence of locations around, kind of a 0.6, 0.4 split for ABG and lobar. They also looked at 0.8, 0.2. We're just gonna put in 0.6, 0.4 into facts today. And like I said earlier, they are using early outcomes, 90-day outcomes, to predict 180-day outcomes. This will be done with a longitudinal model in facts, but we need to assume some correlation between these two outcomes at these two time points. And so what they did for the study was they assumed 0.4 and 0. I think when this study actually ran, and I think Giorgio's on the line, so he can correct me if I'm wrong. He's got a lot more experience with this. But I think when it actually ran, there was a much higher correlation than 0.4 between 90 and 180-day outcomes. So that was kind of an interesting outcome in the data. Okay, Nick, are there any other questions before I flip over into facts?
Nope.
Okay. Let me share my facts screen with you. Okay, so for the last half of the webinar, I want to walk through how this goes into facts, kind of look at what the interesting things in the simulations are, and then I'll tell you what the results of the enriched trial were. We'll flip back to the slides at the end, but let's put the design into facts. I actually have it preloaded in here, but we'll talk through it. Okay, so in the study info tab, by the way, is the resolution okay for this? I know it can be kind of small. I don't know.
It's a little small. I think we can zoom in, but if you could make the whole virtual machine a little smaller, that might be better.
I'm not sure I know how to do that.
That's okay. I think we can read it.
Oh,
That's
there.
better.
Did that help?
Yep. Yep.
Okay.
Much better. Thanks.
Oh, cool. Okay. Okay, so we are in the enrichment engine. This is the continuous enrichment design. And we're going to start putting in our design. So in the study info tab, the design does include a control arm. We're on the utility weighted scale here. So higher utility weights are better. So we've got that response box checked. Utility weight of 1 is the best outcome, 0 is the worst. In general, we're running a superiority trial. We want to know if MIPS is superior to medical management alone. We have an adaptive trial, and we are going to use longitudinal modeling, for that relationship between 90 and 180-day outcomes. There's no cap here. So the groups, I should talk about the groups. These are our subgroups. So ABG and LOBAR. This is our enrichment. These are enrichment groups. You can, in fact, add a cap. So we could cap the number of patients per subgroup. That's not what this design does. It has an overall sample size cap of 300, but we don't cap each subgroup specifically. Okay, moving to group info. We have the option here to add the clinically significant differences that we're targeting. So for ABG and LOBAR, like we talked about earlier, our futility rule, our target mean difference for futility CSD, clinically significant difference, that's that 0.075 that the clinicians came up with. So we put those in here. We're not using any across group rules for futility. The trial-wide futility rule, is both of these two being met. So we'll leave that at 0. I don't know if it matters what goes in there because we're not going to use it. What we will use for the across group row is success. The target mean difference for success, all of our success decisions are based on the across group treatment effect estimate. And we don't have a CSD there because we want to make superiority decisions, not super superiority decisions. And so that is going to be a 0. These three that I'm kind of clicking through, those I don't think are used, so I'm not sure it matters what goes into those there. We're going to leave the phase 3 criteria alone. We're not using that. Visits, this is where we put in our 90-day and 180-day outcomes. So week 13 is going to be our 3-month outcome, our 90-day outcome. Week 26 is going to be our 180-day outcome. And we're not using variance right now. This design has a sample size of, 300 total subjects. I'm sure when they were simulating it, they used this tab a lot to help them decide on what that sample size should be, but we're not going to use that today. Okay, so in the VSR, the virtual subject response tab, we're going to explicitly define our responses. And for each group, we do this separately. So you'll see these profiles are already added in here. But what we're looking at here is adding the control and treatment response assumptions for each of the location groups separately. We're going to leave the control responses at 0. We're not too worried about what the actual control response is. What we are worried about is the treatment response. And we're going to code this sort of as the difference from control. So we're going to leave all the control responses at 0, and we're going to put the treatment effects into this treatment response column. What we do need to worry about for the null, these are all going to be 0 because we're specifying the null profile. What's really important here is the standard deviation. So this is on the utility weighted scale. We're using a standard deviation of 0.338. This was developed, based on historical data, collaboration with clinicians, and so forth. And one thing I always do when I'm using facts is I make a new profile and I forget to update the standard deviation. So make sure when you're doing this, you change the standard deviation in every profile you make. It doesn't carry through. But what you can see here now, I'm setting up the all small profile. Our small effect was 0.15, difference from control. All medium, 0.18. We don't have an all large in here. One that might be really interesting to us is like a null small. So this is where we're going to assume one of the subgroups here, ABG, has no effect and lobar has a small effect, 0.15. Okay, we have these two visits. We have our 90-day and our 180-day MRS. And what we can do here is we can set up the relationship between the early visit and the late visit using with some correlation using this response framework here. So for the longitudinal 0.4 model, this is going to be with that 0.4 correlation that I mentioned earlier that we're assuming between the two endpoints. That's going to go here. So in the middle box, you can see visit correlation. Visit 2 and visit 1 have this 0.4 correlation. We're assuming it for both subgroups. So that's what goes there. The response fraction and the fraction of final standard deviation, you know, if you have some effect that you think is maybe growing over time, at the early outcome, maybe you expect to see half of the treatment effect, and at the final outcome, you expect to see the full treatment effect, set in. You could change these to be, 0.5. If you expect to see half of the effect at visit 1, but with this device, with this trial, what happens is you get the surgery, you're discharged, and the effect shows up right away. And so we don't think that there's a response fraction that's less than 1 at visit 1. So we're going to leave that at 1. It's the same thing with the standard deviation. We think we see the full effect, the full variability after discharge, after the procedure. And so we're going to leave that at 1 as well. And I'll show you, there's some, Giorgio has made some very nice plots that kind of demonstrate this behavior. We can look at that after we move back out of facts. The longitudinal 0 is the same thing, but with the 0 correlation here. Okay, the execution tab, this is where we specify accrual. I've labeled them accrual 5 and accrual 15 because we talk about having 5 patients per month and 15 patients per month, but FACS does not work in months, FACS works in weeks. So we need to make sure that everything we put in is in weeks, even though, it might be nice to think about it with the labels as months. So what you see here is the peak rate is 1.1547 patients per week. That's the equivalent of 5 per month. We do want to assume a ramp-up period of 26 weeks. So I can flip this rate, this peak rate is going to be the week's equivalent of 15 patients per month. The other thing in this accrual tab is the group accrual. And so this is where you specify how prevalent you think each of your enrichment groups is going to be in your population. So we think the ABG group is going to be a little bit more prevalent than the lobar group. So we put a 0.6, 0.4 in here. You can have these on delayed starts. So you could, for example, start the lobar group 6 months later. That's not what the enriched trial did. So these are both subgroups are starting at the same time, but that's where you would put that in here. We're assuming dropout rates of 0 and 10%. So 0 is no dropout, 10% is dropouts per visit. At visit, so we're going to split that, almost equally, relatively equally. At visit 1, we assume 5% of dropouts. Visit 2, this number is conditional. So this is the proportion of people you expect to drop out, given that they have made it past visit 1, that they did not drop out at visit 1. And so in order to get a 10% marginal dropout rate, this value has to be a little bit higher than 5%. That's how we put that in there. Okay, the design tab, this is where those models come in that I was showing in the slides. So in the control model, we're going to use a hierarchical model across groups. This is where we estimate gamma G. So it's the control rate for each stroke location. Those are going to have a hierarchical prior on them. So a common mean, mu gamma, and a tau parameter that controls the amount of borrowing between the gamma Gs. The prior on tau here is going to really, there's two groups. It's going to dictate how much information you borrow. So closer to pooling, closer to independent assessment, that's all set through this tau squared parameter, which has an inverse gamma prior on it. We can come over here to set our priors. What they chose for this study, and this was kind of trial and error, simulate a lot of examples, see what tends to work well, what gives good statistical properties. And what they settled on was a central weight out 0.1 for tau and a weight of 1. So you can kind of think of this as like one location's worth of information placed on a central weight of 0.1. When we add in the treatment effects in the treatment model, we still have these gamma G's showing up. Those are the control, kind of the baseline control rates in the control group. And then the treatment patients get an additive term, theta G. The top equation here, this first Y, this is our interim analysis model. This is the hierarchical borrowing. Each location gets its own treatment effect estimate. The theta G's, again, have a hierarchical prior distribution on them. So tau squared is going to dictate the amount of borrowing that happens between the theta G's, the location treatment effects. And again, they ended up using the same prior on this tau in the treatment effect structure as they did on the other tau in the control group borrowing on the gamma. So that's a 0.1 and 1. The other model that's down here, this Y, the second Y here, this is theta across groups. So this is when you pool all of the data, you estimate a single treatment effect, theta AG. It's still going to be added to this group-specific gammas, the group-specific gammas, but we're just estimating this one treatment effect, theta AG. That comes from a normal distribution here. The prior we put on theta AG is pretty diffuse. That's this across group prior here. We're going to center it at 0. That means no treatment effect, and put a wide prior on it. So that's where that gets entered in. For the error parameters, we have some idea of what we think the variability in the study is going to be. So we're placing a central weight on the standard deviation parameter of 0.36 and a central value of 0.36 and a weight of 1. Okay, we're not using the frequentist analysis, so we'll skip that. The longitudinal model here, this is a kernel density model. And so, and Nick and Tom might have to help me out with the kernel density model. But what this model is going to do, and you can kind of look at the picture down here, is on the x-axis is representing the response at the early visit. On the y-axis is representing the response on the final visit. So you can think of this as 90-day and 180-day utility-weighted MRS outcomes. Of course, the picture's not on our scale, but that's the way you can think about it. And so what we do with the longitudinal model to try to relate early outcomes to late outcomes is we use this kernel density approach. And so what happens is if we have a subject that has an early response, and let's say that early response is right exactly at this triangle with the dotted line, what this model is going to do is it's going to assign probability to each of the points on here, which are patients who have observed both responses, early and final. And it's going to say, okay, which of these points is most likely to be, close to where I'm at. So in the x-axis. So it assigns probabilities moving left and right. It selects a point, and then it says, okay, now I know there's some variability up and down. Sorry if I'm butchering this. The FACS team may be cringing. There's some variability up and down, and now let's multiply impute a value, and let's sample a value based on that distribution with the variability on the y-axis. And we do this over and over again. So we pick a point that with some probability, based on the proximity on the x-axis, we know there's some distribution in y, and we generate an observation from that. And we do it again and again and again. These values for this kernel density model, these are, so what happens, there's these parameters H and Y, H, X, and HY. And they dictate, the distributions side to side and up and down here. And those will be estimated. FACS will estimate those for you. What you need to do up here is say, what is the minimum number of subjects that I want to use for that estimation? And we put 6 in here. I think these are the defaults, 6. And if there's more than 6 points, blue points on here, FACS will estimate H, X, and HY for you. It's fantastic. If there are less than 6, then it is going to use what you put in here for H, X, and HY. And if you remember, we're not going to be doing interim analyses unless we have a minimum number of subjects with complete data. And so we're not going to run into this situation. So these are just left at the default values.
And I will say that we have made that more explicit in FACS 7.1. So the inputs will actually define and describe what happens. So it'll be more intuitive.
Okay, thanks, Nick. Okay, allocation, we're doing 1-to-1 randomization, no response adaptive randomization, nothing like that. So we're using block sizes of 2 for our equal randomization. For our interims, we've added them all in here. They go 100 to 300 in every 25. What we're going to do is we're going to follow subjects after they're stopped. These trials, I think with enrichment trials, you're going to tend to post-process the results. So it's nice to see what happens. Oops. No, I want to keep my simulation results. What tends to happen is with these enrichment trials is you post-process to get some of the nice operating characteristics that you want to look at for your specific study. So you can kind of see what happens after patients after the trial stops for futility. Okay, and then we'll go through this briefly. This is the success futility criteria. This is a big one. Okay, so at the interim, we're going to use the same criteria at interim 1 as we are at all the other interims. The rules aren't changing. We have futility criteria. It's based on these posterior probabilities. So we've got the groups in here. Our futility criteria, we can stop with ABG group, with low bar group. We stop if that posterior probability that the difference is greater than the CSD is less than 20%. So that's where those 0.2s go. The CSDs here are the 0.075s. We input those earlier. And this is where we're specifying our overall trial futility rule. Stop the whole study if all of these selected subgroups stop. So that will stop the whole study for futility. And again, we've got this minimum number of subjects that we need to reach the final, we need to have their final observations before we allow the subgroup to stop for futility. So 30 and 30. So that's the enrichment piece, the trial futility piece. We have success criteria. Our success criteria is all based on the across group estimation. So we can enable early stopping for across group treatment effects. In order to stop the study early for success across groups, we need that posterior probability to be greater than 0.99. That was that kind of overwhelming efficacy signal. The CSD here is 0. And that's going to stop our study early for success. So here, I think you can put this 60 in either spot. So the minimum total subjects before study can be stopped for success. That 60, I think that's the same thing. You could put it in here too. I think these do the same thing, but that's where that goes. At the final evaluation, our primary analysis is based on the across group treatment effect, and we compare that to 0.975. If the posterior probability is less than 0.975, we consider it futile at the primary analysis. If it's greater than 0.975, we consider it successful at the primary analysis. And so that's what's set up in these two here for the final evaluation tab. Okay, and that's pretty much it. That's how this design goes into FACS. I've got a couple, and there are a lot of simulation scenarios here that you can see with all of those different combinations that we put in. I've got a couple a couple simulated that we can look at. You can see the average number of subjects ranges somewhere between 170 and 240, just based on the few things that I've simulated here. So I think for this, it's actually more interesting. Oops, sorry. To look at, so you can see the proportion of trials with the success criteria met at the final for ABG and lobar. Those are going to be those group specific parameters. This across group, this is our power. So the proportion of trials where the across group treatment effect met its success criteria. In this scenario where we've got a small effect on one subgroup and a null effect on the other, that's got 77.5% power. So let's look at this. Can you see the pop-out box when I click on that?
Yes.
Nick or Tom? Okay, thanks. So we can look at the simulations file here. So you can look at the different simulations on their own. You can see a lot of these stopped a lot of these trials stopped the lobar group for early futility. So you can see a lot of early futility in this lobar column. Continuing to randomize to ABG within the ABG location, you can see a lot of these met late success. And so you can kind of look into those. One other nice thing to look at here, you can open the weeks file and you can see for this specific trial across all the interims, what happened. So the lobar group hit futility right away. It was futility. The ABG group stayed in the trial until it met the study cap. Then here the lobar result was early futility and the ABG result was late success. So those are some nice ways to look at this. You can load all these files in for post-processing there.
Oh, we have two questions. Yes.
Okay, yeah.
Okay, so the first one is there an analytical formula for sample size calculation in enrichment designs, particularly if one wants to use a frequentist approach? I didn't know the answer to this, so pass it off to you.
Oh boy, I don't think I know the answer to that either.
Yeah.
Sorry.
I'm guessing under certain assumptions there is, but maybe not for something like the enriched trial. Okay, so
yeah,
we don't
there
know.
Is a paper. Yeah, there is a paper. There is a paper. Oh boy, I'm not gonna be able to remember it. Whoever sent that question, feel free to send me an email. There is an analytical control, I think, in a frequentist approach. There's a paper that came out not too long ago that I can dig up and send you. And I'm not going to be able to remember the name of the trial right now, but it's ringing a bell. But feel free to reach out.
Okay. The next one was about the potential for a subject to come in that is in both subgroups. And maybe that's not possible in enrich, but do you have any intuition as how you could handle something like that, a subject that maybe is both lobar and ABG, for example, and how enrichment could work in that case?
Yeah, that's an interesting question. I know it's almost more of a basket trial question, I think, but that wasn't possible in enrich. And so in facts, and Nick and Tom may be better off answering the question about whether facts can handle something like that, but I don't think that's possible. In enrich, with this hemorrhage, it's either in an ABG location or a lobar location in the brain. So patients in this trial couldn't come in with both, for example.
Okay, one more.
Okay.
If you enrich, why do you claim success based on the posterior probability in the overall population, but not in the selected population? Oh.
Yeah, it's a good question. And it's really, sorry, I'm trying to do two things at once. It's really because when we use the overall population, when we used all enrolled, it gives us strict control of type 1 error. So this was sort of the difference between these two analysis strategies. It's definitely more natural. It would be more natural to test just the remaining subgroup But that, again, comes with some cherry picking, increased chance of type 1 error. So when you use all randomized subjects, you use the across group treatment effect estimate, you might get some dilution based on, including patients from a dropped subgroup, but you get this nice statistical control of type 1 error in the joint null scenario, which is something that we worry about.
And I think that actually goes back to the question about analytical control of type 1 error, in that if you do analyze the entire population at the end, you don't have to worry about the type 1 error adjustment, the alpha adjustment.
Mm-hmm. Yeah, right.
So there's an easy way to get analytical type 1 error control.
Yeah. And the paper I was talking about takes this approach. It's a really structured version of enrichment, but there is some version of analytical control in an enrichment trial. But I think it's like a single enrichment step, and it's got a lot of assumptions behind it.
Yep. And one more question, and maybe this is for Giorgio, I'm not sure. Can you review why we didn't use posterior predictive success for early stopping?
Yeah, I think this is an interesting question. I'm guessing it's about posterior or predictive probabilities, I would say, as a quantity of interest to look at. It doesn't always perform that well in enrichment, and Amy and I both had experiences where it sometimes doesn't enrich as much as a general rule, and so posterior probabilities work better. That said, it could have also been designed probably with calibration using predictive probabilities. I'm not saying that one approach is necessarily better than the other, but I think that was the reason why a posterior probability of superiority was used.
So I will say, I think this is interesting. This trial Ben mentioned was designed in FACS 4.0. So it's an old one, but a good one. I'll just mention really briefly what the trial did. I know we're over time. The trial, it did its interim analysis at 150, continued randomizing to 175, where the futility criteria were met for the ABG subgroup. So that super superiority rule with the clinically significant difference, that posterior probability dropped below the threshold of 0.2 at this interim analysis, and accrual was halted to that subgroup. Accrual continued in this low bar subgroup, the purple, all the way until the end of the trial. The trial was successful, so the superiority rule on the across group effect, which was estimated at 0.084, was 0.9813, so above 0.975, so successful primary analysis. You can see the accrual plot. The orange and the green are the two locations. You can see green stop, that's where it was dropped for enrichment, and you can see orange continue. The black line is overall accrual. When we stop one of the subgroups, accrual kind of slows down, which is expected. And I'll stop there.
I think we got through everything.